All right, we have two more talks for this afternoon session. Next up is lun-Jun, who's telling us about synergizing Roman and line intensity mapping.
Hello, everyone. My name is Simon lun-Jun. I am a sixth-year graduate student at Caltech, and today I'm very excited to talk about our efforts on exploring the synergy between the Roman galaxy surveys and the line intensity mapping, this new statistical probe. And this is actually part of the Roman White Field science project of reionization science from the cross correlation with Roman and PI. Our PI is Adam Liz, and I'm very happy to work with our fantastic collaborators. And today I'll essentially talk about the impact of the bursty star formation and in the early universe. Okay, let's get started. And so to begin with, our theme is to study the epoch of reionization. I will highlight this is a very important era to study is because within the first billion years of the universe history, the first stars and galaxies form, and the radiation started to ionize the surrounding neutral gas. And then, at around the first billion years, these ionization process sort of ended and becomes, the universe becomes fully ionized. So that's how we are very particularly interested in study this epoch, is because, for example, we wanted to understand the reionization history in this epoch. For example, also we wanted to trace, for example, the growth of the ionized bubbles in this epoch. And we also wanted to learn about the star formation, galaxy evolution in these critical early epoch. And, for example, wanted to answer whether it is a few massive galaxies that are dictating the cosmic star formation within this epoch, or it is mainly the lower mass galaxies that are more abundant in charge of the cosmic star formation. Okay, so having been said, I want to highlight that Roman is of particular interest and showing its unique capability of probing the early universe in a way that, as you can see, we really wanted to get a large enough sample for us to study this epoch. And so Roman is really opened this window by performing this crucial galaxy surveys. One of them is the high latitude wide area survey, the medium term, which is important, about 2,400 square degree. And there's also the deep tier, which is about 20 square degree. And this really opens this massive cosmic volume because, previously our understanding of this early epoch is, for example, essentially through GWST, which is very limited by their small field of view and small survey size. And for example, for a quick comparison, one of the largest GWST survey is only about like half a square degree, which Roman is bringing this, tens or hundreds of thousands of boost of the survey volume. Okay, so how are we going to use Roman to search for these ultra high redshift galaxies during this reionization epoch? So here we are using this Lyman break method to search for these galaxies, which essentially, if you're looking at the examples here, we can find that depending on the redshift of this galaxy, you may find a non-detection in one of the filters, but in the next two redder filters, you'll be able to see significant detections. That's how you can get these candidates up to, for example, redshift 11, up to like the F184 filters, and also depending on the reddest filter, which is F213 sensitivity, and you may be able to measure the brightest galaxies up to redshift 14. Okay, so one critical thing one critical puzzle, I would say, in these early galaxies is that we sort of found that the intense episodic burst of star formation prevails among these galaxies, and which can be seen, which is essentially, I would say, this bursty star formation is very highly timely, time variable star formation history of a galaxy's evolution history. And so here I am showing one model we're making, and to really tell you how this episodic bursty star formation would look like. So in this model, you can see these individual episodes of the star formation. And in this model, we are essentially inputting the delayed supernova-driven feedback that dictates this episodic star formation. The idea is essentially that, in individual episode, star formation is very efficient, while the feedback is not strong enough. And then, once the stellar evolution moves to the supernova phase, and the strong feedback efficiently expel the gas reservoir and shut down the star formation. And then you allow for these individual gaps to allow for this galaxy to reaccrete gas and then reforming the stars for the next episode. Okay, so this sort of picture has been formed in the pre-JWST era, and we are sort of finding more evidence kind of like supporting this picture. For example, as shown on the right, presented by Deluser et al. 2023, where he built a sample of redshift above 6 galaxies, and by studying the recent starburst indicator, they find that most of the galaxies are showing this recent burst of star formation. This is one interesting support, and also JWST reveals an overabundance of the early UV bright galaxies. This could also hint for this bursty star formation history. Okay, so I'll talk about this in this slide. So with the discovery of this overabundance of the UV bright galaxies at high redshifts, so we wanted to study how they distribute, right? So one way is to plot their luminosity function in the ultraviolet. And so shown here is the redshift 10 UV luminosity function. And by comparing with data and let's call it the non-bursty model, we find that our non-bursty model is essentially failed to explain this observed UV luminosity function. And while we impose this bursty star formation model, we are sort of able to reproduce the observations. This is quite natural for this understanding is because, as you can see, given the time variability of the UV magnitude, the upscatter of this UV magnitude sort of like dominates and then so naturally boost the bright end of the UV luminosity function. Okay, so with these model built, so the idea is to trying to constrain whether this picture is true or not, right? And so we really wanted to get access to the bright end of the UV luminosity function to really test this theory. So as I'll show here, as I'll stress as well, like Roman is uniquely opened this window to really probe the bright end of the UV luminosity function. And for comparison, if we're also plotting the regime of the Cosmos Web, we are still limited down to the intermediate UV magnitude. And once we're getting to the deep tier of the Roman survey, we started to open up this window, and even through the medium tier, we can really probe the very brightest end of this UV luminosity function, which is great, right? And so given this capability, so the next part I really wanted to talk about is the number density one of forecast for the upcoming Roman galaxy surveys. So here, again, I am dividing into two scenarios. One is the medium tier, which is the one of the largest survey area, and the other one is the deep tier, which is about like 20 square degree. And again, like by comparing the bursty and non-bursty models, we are able to see that starting from about like redshift greater than 8, we're seeing that this bursty model is gonna boost the number of Raman detectable galaxies number counts by up to like a factor of 5 or up to 10, I would say. So which is great. This is because, as I'll mention later, this will be very helpful for studying the statistics. And okay, so here is going to be one of our main predictions here, which looks quite promising, and we look forward for the Raman galaxy surveys to really measure these numbers of high redshift galaxies. Okay, so the next part I'll quickly talk about is we wanted to explore the synergy between the Raman galaxy survey and this line intensity mapping measurements. So line intensity mapping, or LIM, is an emerging new technique that tries to efficiently map the 3D galaxy distribution within the large cosmic volume. So instead of trying to spend much time on resolving individual galaxies, line intensity mapping measures the aggregates of emission from all galaxies. So this will make it very efficiently to map the structures and galaxy distributions within the cosmic volume. And so the synergy here is that by measuring this aggregate, we're not just including the signals from bright galaxies, but also those coming from the faint galaxies that are just unable to be resolved by the traditional galaxy surveys. So by building this synergy, we are not just be able to further understand those resolved galaxies, but also information from those faint galaxies. Okay, so basically when we are studying this LIM, line intensity mapping statistical probe, so the one way to study that is by studying the Fourier transform of the Fourier transform of the two-point correlation function, which is sort of like shown here. So I will just quickly walk through. One of them is to studying. I'm plotting this power spectrum, the Fourier transform of the two-point correlation function, and we're seeing that if we're imposing this bursty star formation model, we'll see this visible distortion of the power spectrum shape that just cannot be explained by the non-bursty models. And on the other hand, if we are building this cross-correlation from the Raman galaxy counts with a tracer of the 03 88 micron line intensity mapping, we are also be able to see sort of like the boost of the Poisson noise term of the cross power spectrum. And so these are the effects where you can see that this synergy within this bursty star formation model is really bringing up this capability of constraining all these statistics by, for example, boosting the signal-to-noise ratio by a factor of 10, let's say. Okay, so with these preliminary constraints, the next step in my study would be, for example, we can furthermore study the clustering analysis of these early galaxies. One, for example, there's the Pioneer study by Niels et al. In 2023. But I also want to mention that when we are measuring the brightest galaxies in these ultra-high redshifts, these galaxies could enter into the nonlinear regime. So we want to really to constrain that whether this joint analysis between Raman and line intensity mapping is able to both constrain the linear and nonlinear galaxy bias. And also we can use this cross-correlation to study the growth of ionized bubble through, for example, the cross-correlation with the 21 centimeter line emission. Okay, so having mentioned all these, I'll just leave my summaries here, and I'm happy to take your questions.
Thank you. We have gone into our question time and beyond. So maybe, is there a quick question? All right. Oh, one. If it's very fast, right here.
How much time are you allowing a supernova to quench a galaxy in?
Well, within the few 100 million years, that is going to be. I mean, that's at least what I have shown in the model I've shown before. That sort of, ends the per se shut down the star formation within this time period. Yeah.
Okay, let's thank lun-Jun again.